Hi there, Rachel Sherman here, and in this video we're going to explore the vocabulary behind relations on sets. If you watched the previous videos, we learned a little bit in those about functions are always relations, but relations are not always necessarily functions. So here we're going to look at the other side of things. A relation can be defined algebraically or really any way. It just depends on what your domain and codomain are. So take, for example, this relation, let's call it L, from the real numbers to the real numbers as follows. For all real numbers x and y, we read this as x is related to y if and only if x is less than y. So you'll notice in this case we're dealing with something that is specifically algebraic. So just based on this inequality alone, let's take a look at a few examples. Pause the video and take a few seconds yourself to determine which of these is considered a relation and which one is not. Now that you've had a chance to try those, let's take a look at each one. You would read this as 27 is related to 15 if and only if 27 is less than 15. This would not be part of the relation because 27 is not less than 15. And then you're going to repeat that process for each one of these. -7 is less than -3, so we can say yes, this is true. 344 is not related to 344 because it's not strictly less than. So 344 is not less than 344. And last but not least here, -11 is in fact less than 2, so yes, this is a member of the relation. Now, this relation itself is dealing with uncountably infinitely many things that work for it. If you look at the inequality x is less than y, when it's defined over the real numbers, so another way of thinking about this is reals crossed with the reals. When you're dealing with two uncountably infinite sets, domain and codomain, that means that when you take their Cartesian product, there's also going to be uncountably infinitely many things that could be part of the relation, and we would have to check every single one. Now, if you think about what this looks like graphically, you may find that it's much more easy to determine what the relation will look like. So if you recall from your algebra days, x less than y, you would treat this as what does the graph of x equals y look like? It's a 45-degree angle, and then because it's strictly less than, you're going to use a dotted line. So take a moment and graph that. Now that you've had a chance to graph your dotted line, now you have to check where this will be shaded. You're going to pick a test point that's not on the line. Let's say, for example, 3, 0. Is 3 less than 0? No. So that means we do not shade below, instead we shade above. What we can see here by finishing this graph is that anything in the shaded region is going to be considered part of this relation. So in other words, this relation would be true anytime it's in that shaded region. Let's take a look at another example that incorporates power sets as well as cardinality. Let some set R be equal to 1, 2, and here's the power set. So if you weren't provided that, then you would go ahead and find the power set of that value. Remember that power set represents the set of all subsets. Define a relation S from the power set to the integers as follows. So our domain is the power set, the codomain are all integers. For all sets A and B, A is related to B if and only if A has at least as many elements as B. So let's think about what that means in terms of cardinality. That means the cardinality of set A at least, well, at least means greater than or equal to the cardinality of set B. So in other words, if you treat each one of these as A on the left, B on the right, and you check the cardinality, you'll be able to determine if it's a member of the relation. So let's take a look here. We have empty set has a cardinality of 0. 1, 2 has a cardinality of 2. 0 is not greater than or equal to 2, so we would say no. This is not a member of the relation. And you're going to repeat that process for each one here. So take a moment, pause your video, and try these on your own. Now that you've had a few minutes to look them over, finish out the rest. So we have a cardinality of 2 and 0. 2 is greater than or equal to 0, so we can say yes, this is a member of the relation. More specifically, if you're curious, it's referring to this as an ordered pair being an element of the relation. So that would be the set 1, 2, comma, empty set. So this would be a member of relation R in this case, or I'm sorry, relation S in this case. Repeat the process. We have a cardinality of 1 and 1. 1 is in fact greater than or equal to itself, so yes, this would also be a member of the relation. And same thing here. These both have a cardinality of 1, so this one works as well. The last thing we're going to look at in this video is how to clearly state the relation and also the inverse of a relation. So if you're given any relation, technically the values that you're checking all come from the Cartesian product of your domain with your codomain. So take a moment and calculate all of the ordered pairs that would come out of A crossed with B here. Now that you've had a chance to write out all of your ordered pairs, check them one by one to see what works in this relation. So this is the divides relation. X is related to y if and only if x divides y. So let's come over to our list here, and these are the 9 different ordered pairs that we have to check in the relation. Ask yourself, does 2 divide 2? If the answer is yes, then we can say that it's part of our relation. If the answer is no, then we ignore it and we move on to the next. So in this case, relation R is going to be defined by the values that this works for. 2 divides 2, so we would include that in relation R. Ask yourself the next one, does 2 divide 6? 2 does divide 6, so we add that to our list. Similarly, we're going to keep going. We know that 2 divides 8. We check the next. 3 does not divide 2, so we skip it. 3 does divide 6. 3 does not divide 8, so we skip it. 4 does not divide 2. 4 does not divide 6, but 4 does divide 8. So these would be the 5 values included in our relation. The inverse just means that y comma x is how you're defining these instead. So you're saying that if xy is in the relation, yx is in the inverse relation, and that's an if and only if correspondence. So how would you determine the inverse relation? By flipping all of your x's and y's around. So we would still have 2, 2. This one would be 6, 2, 8, 2, 6, 3, and 8, 4. So there you have it, your relation and your inverse relation. Now, the more of these you practice, the more savvy you'll get with these kinds of things. You don't necessarily always need to come up with this full comprehensive list, but especially when your domain and codomain are smaller, it can make it a little easier to understand, at least for the first few examples that you do. If you continue watching these videos, you'll definitely see more involved examples on when it would be beneficial to not spend time writing out this list. So I'll be teaching you some tricks in upcoming videos. In our next video, we're going to explore directed graphs. Thanks for watching.